in the sensing with photons. So it makes a lot of sense to do sensing with photons because that was what optics was good at. But the computing with optics has always been a little bit controversial. It started like more than a century ago, but there was a lot of interest in the late 70s, 80s of using optics to do computing. But then at the time, like semiconductors scaled really well. So then only until recently, people start to be interested in the potential of optical computing again. And so the question is, we want to ask is like, why? What's the difference this time it makes? And what the limitation of other like conventional computing platforms, and what does optics do differently? So today's work is mostly still done at Cornell with all the people contributing to the content I'm going to talk about. But also I want to say that for the content I covered today, my own lab is continually working on some of the topics, and I will expand a little bit on my own lab's work a little bit later on. So the first question we ask is that, why do we want a new computing hardware? Aren't we already good enough with all the GPUs and semiconductor computing hardware? So like at a high level, if we look at back into the history, we can see that actually the computing hardware is important. It's the computing hardware that shape our software, and that's also the computing hardware, the available kinds of computing hardware that limited our creativity in software. For example, the example here is just say, neural networks have been around for a very long time, in late 80s, 90s, but it only started to take off when GPUs became available. So when GPUs became available, people could use a lot of data to train large enough neural networks so that their performance started to approach human performance or start to be better than any other alternative machine learning models. So this is exactly the kind of example is that, it's the hardware that shaped our point of view of whether it's a good software. And of course, therefore, we wanted to develop on the hardware side. To give us more possibilities in software. So, and still since the first like demonstration of AlexNet with neural networks, like this field has been growing rapidly, leading to so-called the training scaling law, which means that the models are growing at a very fast speed in terms of parameter size and the computational numbers. And this the speed at which these models are growing is much faster than the speed at which the computing capacity of hardware are scaling. And here is a log plot in the log scale in the vertical scale, which means is that a difference in slope means a difference in growth rate. And then the efforts in like developing like application specific hardware only serves to offset this trend line, which means it's multiplied by a constant factor, but not really changing the growth rate. So therefore, like the way for people to close the gap between the model size and the computing hardware capacity is only to put more hardware there, try to make larger clusters. So therefore, there's indeed incentives to make like fundamentally different hardware to close the gap. And then that's why another reason why it prompts us to think of more creative solutions in the hardware domain. So what kind of a hardware are we thinking? Why do we think about using like analog systems for this kind of a problem? I think used to take a little bit of time for me to explain, but this year's physics prize, like Nobel Prize in Physics, made it much easier for me to explain. So to many people's surprise, the physics prize was given to artificial intelligence. But if you read the reason why it was given to it, it actually makes a lot of sense. It's given for the contribution to borrowing tools from physics to enhance the performance of artificial intelligence models. Here is just give a illustration of how the neural network. But really, what the underlying message is giving is that the physical systems are doing computing in a not quite the same way as digital computers, and there are still things we can learn from it. Of course, quantum computer is one example that it does differently from digital computers. So what are physical system processing information differently from digital computers? I think here are several notable differences we wanted to be aware of. So on the left is like basically the von Neumann architecture of the classical digital computer. The outstanding feature of this is that it features centralized control, centralized processing, and centralized memory. So the processing unit needs to have access to all the data in the memory, and then the whole the flow of processing information is controlled by a complex set of pre-programmed algorithms. This is like the software engineering we are familiar with today. And then the whole machine is based on a mathematical model. It's based on symbolic reasoning, so it has finite and discrete internal states. Like 0 is 0, 1 is 1. There's nothing in between, and it's discrete and finite. But on the other hand, the physical systems, including artificial neural networks or biological neural networks, they process information in a quite different way. So you can think of them a larger physical system composed of smaller parts, and they are just interacting with each other. And for each part, it actually has only access to very little memory and very little information. It doesn't have the whole picture of what the system is doing. And then they interact with each other according to very simple local rules. So they can only also do very simple operations. So this is really operating in a very decentralized manner. Like our biological neuron, you cannot find a neuron that really knows what we are thinking about. The so-called grammar neuron is just it's coincidence. It's not like say each neuron knows what the task they are part of. But it's just this kind of a system that, once you set up in the right way and you let it evolve, it can assimilate information from the data so that it can start to perform like complex tasks like pattern recognition. And this is essentially the underlying idea of machine learning that leads to revolution to today's artificial intelligence. And that's another interesting feature of a physical computer system we wanted to be aware of is just that they are always analog systems, like almost exclusively analog system, and also they comes with noise. Sometimes that's the point that most people neglect. They think of analog computing as like smooth, like real number computing. No, it always comes with a noise. In room temperature, it comes with thermal noise, and even if you cool down to close to absolute zero, there's a quantum noise. So, and the noise is actually an essential feature of these systems. So here are just some differences, and to give you an idea on like what kind of a regime we are interested in. And after seeing the difference, it's very easy to understand why we are thinking about this, because the physical system is exactly the kind of system that inspired artificial neural networks. Then the question is that why should we use a digital computer to emulate a physical system instead of just directly using a physical system to run the algorithm, right? So, that's really inspired us to work in the broader field called the physical neural networks. It's essentially figure out the ways, what are the good physical systems to act like a machine learning processes, and how to tame these systems to behave the way we wanted it to, right? How to improve their performance for certain tasks, like in terms of like training. So this was the work done by my colleagues, Logan and Hiro. We were the postdoc in the same lab in Peter's lab, and so they did a great work on proposing a new, demonstrating a new algorithms for training physical systems in a quite arbitrary way. So today, my focus is actually on using optical systems as neural network systems. So, just give you a simple argument on what is attractive about optical system as a neural network processor. So here's a very simple example, and here I think everyone knows what it is. It's a single lens doing a Fourier transform across its focal plane. So, and this thing, like we learned a long time ago, but there's something strange about this, which is, it's doing Fourier transform, and we can discretize it at the emitter and the receivers. And so if we count the number of emitters, we say there are n emitters and n receivers. And these are the part actually we need to consume energy to operate, right? So for emitters, we need to emit light, modulate the light. And for receivers, we need to spend energy to power the detectors and also like convert analog to digital signals. However, like the discrete Fourier transform performed between them, it scales with n squared. There are n squared elements that in that discrete Fourier transform matrix. That means there's n squared multiplications and additions. So then you divide the energy consumption by the amount of multiplication that is done, because this like multiplication happens passively, right? This optical diffraction is lossless passive time reversal process. So then you see the amortization when you try to divide the energy. So that means that the amount of energy you spend on each multiplication scales inversely with the dimension in this emitters. So and then you get this 1/n inverse scaling. So and that really means that the higher dimension we are processing, the more energy benefit we can get, and it can almost be infinitely small. Can it be? Actually, no, because at some point it must break it down. Like when your n is large enough, it is possible at some point that you're using the energy for less than 1 photon. And in that case, we cannot deal with mean field anymore. We need to deal with quantum effects. So the first question is when does it break it down? And then for within the regime that still holds, can we leverage such kind of a scaling to make a practical device that can achieve optical advantage? So yeah, just say a couple words on optical neural network or photonic neural networks. This is the field that really concerns implementing quite arbitrary linear transforms between vectors. So before I showed like discrete Fourier transform, but that's like a fixed operation. And in computer science, people know that you can do Fourier transform, faster Fourier transform with n log n, which is quasi-linear. So really, what is hard is arbitrary linear transforms, and that is the majority of computation in artificial neural networks these days. So in other words, if you can do this part very efficiently, you can reduce the entire energy of AI models by large orders of magnitude. And there has been tons of work done in these areas, using free space, diffraction, on-chip silicon photonics, and fibers, and also like frequency, spatial temporal multiplexing, trying to achieve different kinds of ways to do linear processing with optical modes. The modes can be spatial modes, frequency modes, or time and temporal modes. But they share the same like underlying principle. Basically, all these optical neural networks, they are analog computers that need to deal with noise. So back to our questions, say, we are envisioning this optical scaling law, which says that even though for low dimension, optics is more expensive in energy consumption compared to electronics, because there's like overhead in analog digital conversion and also in optical electronic signal conversion. But as we achieve large enough n and our scaling law, if it holds, then it will cross over with electronics so that the overall system energy would be lower than electronics. So to make sure this happens, of course, there's a lot of engineering to be done, but there were fundamental questions to ask. The first is that when does this scaling law break down? Right? It may break down before the crossover happens, and also it's like when in this regime, can we make any useful models work with optics? So, and then my work in the past just like was centered around like these two questions. The first question is like, when does this break down? So actually, the practical way to show it is just through experiment. So why does it break down? It's because of the quantum effects, and most simple effect is just the short noise in photon detection. So right here, a lot of you are very familiar with the high photon counts. It's a SNR, signal to noise ratio, is high for the Poisson distribution. But with low exposure, light exposure, then it's the same Poisson distribution, but the signal to noise ratio is lower. And this is like something everyone knows in imaging, but it applies to optical computing as well. It's the same kind of a noise, like deteriorates the performance of optical computing. So Theoretically, people have tried to predict that to what limit it can be achieved, and say actually when the dimension the number of the vector dimension is high enough, like even around 100, like we are already at a regime that can consume less than 1 photon for each multiplication, and this also corresponds to energy consumption that is lower than so-called Landau's limit in irreversible electronic computing. Basically, say you have an irreversible logical gate, that reduces the entropy of your system. Therefore, it consumes an irreducible amount of energy. And but for optics, it's like if we are running at a high enough dimension in linear processing, actually we can even beat Landau's limit. It's interesting to think about, but I don't think that there's really a lot of implication, because for electronics, you can make it reversible as well. Reversible is basically saying, like, you look at there's no information loss in the end results. You look at the end results, you can find a way to reconstruct the input. Say you add the two numbers, like you get a 2, 1 plus 1 equals 2. 0 plus 2 is also 2, but you just look at the 2. You don't know which two numbers you add together. It's reversible, right? So
by beating the Landau limit, you're implying that the optical case is reversible somehow.
Yeah, and that's the nature of optics. Just say in lossy situations, it's like a reversible system, time reversible system. So, yeah. So this is just like interesting in the physics point of view. The first time when I read about this, it was like, okay, I want to know if this can be actually realized in a lab, right? So that's the incentive behind it. This is all theoretically, say you can use less than 1 photon for each multiplication. So yeah, that was the first experiment we did. We just did a free space optics experiment. I would say there's not too much details. The really hard part is the precise engineering, which like you guys know very well. Since we try to do like pixel to pixel alignment and to do element-wise multiplication, and then this is the kind of thing we do. We multiply each image pixel with different modulating weights, and this is like the actual data got from our system. We engineer a system that has high enough dimension up to 0.5 million, which is good enough so that we can test that when the n is very large, how the scaling changes. So, and this is just the principle showed it more clearly. It's essentially just say we have a vector we arrange in 2D and we make a copies of it. It can be optical copy. Later I will show you how to do it. But then you just modulate each copy by a different weight. And then after you get the modulated copies, you focus them into detectors. And that's how you get the vector dot product. Right? Here is like a Hadamard product or element-wise product, and then you add them up, you get the vector dot product. Correspondingly here for each block, you just focus the light onto a detector. That's how you get it. So, and then we just use this setup to run like a simple neural network model classifying like handwritten digits. So here it's like just the 4-layer fully connected neural network, and all the optical operations were done with the setup. The only digital operations that was done was the element-wise nonlinearity and bias. And then we use some special training techniques to train this optical neural network. It's called quantization aware training. And with this training method, it's quite critical to make the optical neural network to be robust against any hardware imperfection and noise. And with this neural network, we have been able to show that it is possible to use even less than 1 photon for each multiplication to achieve 90% of classification accuracy on image classification. Of course, if we increase the energy, it gets even higher. That was just to my surprise, to be honest, that this could actually be achieved in the lab. And just give you a sense on what kind of optical energy this is. It's corresponding to like a total of 100 femtojoule optical energy to run the entire neural network once, which consists of about 90,000 multiply and accumulate operations. So in comparison, give you a sense that if you multiply to 8-bit integers, on 7 nanometer nodes electronics, it costs 70 femtojoule. So that's like many degree orders of magnitude difference in these two. But I wanted to stress that in electronics, you count all the energy consumption, but in optics, this is purely just optical energy. If you count overhead, typically now it's still pretty high, but it shows the fundamental like a potential, in case one can make a perfect hardware for these systems. But rather than this energy consumption, what is more interesting to me is just really gives us a guarantee that this optical scaling can hold even at a very low optical energy level, and that safeguards a lot of later work. And also it shows us that this optical neural networks can be intrinsically very robust, resilient to noise, which the way they should be for analog computing systems. So just a quick word on what it means by less than one photon per multiplication. It's actually quite straightforward. Since we are focusing photons from many spatial modes, so the number of photons we detect is an integer number, but we divide it by the number of spatial modes, then it becomes fractional. So that's why it can be less than one. So it's a like expectation value. It's not like say on any given shot of measurement we get like fractional number of photons. And then here we just want to really stress that like in most of any work before ours, people think of optical neural network or other analog neural network as like continuous variables, right? You just have continuous variables, you multiply them. But really the right way to think about it is that you are feeding a noise distribution into your systems, and what you are reading on is also a noise distribution, stochastic variables, right? And this way of thinking is like connects more smoothly to quantum systems as well. But in our case, it's luckily it's like there's not much quantumness. It's just every photon is quite independent. It's a weakly attenuated thermal state, which is close to coherent, and the output has quite a high signal to noise ratio that ensures the good performance overall. But later on, we push the limit a little bit more, like by 100 times. So later on we further like reduce the optical energy by improving the training method. So to be more specific, the first work I show is like where the input is stochastic, but the output is like has high signal to noise ratio. But later on, what we do is like we further reduce the integration time so that even the output is stochastic, like we're getting 0 or 1 photons on the photon detectors. So therefore, the input and output both become quite stochastic. And it's getting closer to like a spiking neural network kind of regime. So here, just give you a kind of intuitive understanding on what's going on, because people say, well, if you are doing classification tasks, like how can you work with a stochastic neural network, right? Like, won't your results change from trial to trial? So this is how it works. We have input, we have a bunch of neurons, and here we have a single photon detectors, SPD. And for each of them, like they are actually counting 0 or 1 at the most 2 photons. And then this on given trial, we are getting like 0, 0, 1, like a random like vectors. But there's one last layer that concentrated the light a little bit more, so that we are getting non-binary readings as the last layer. And then we repeat, and here it shows the right classification results. And if we repeat the experiment, so this the intermediate, the hidden layer can change a little bit because it's stochastic, but the output changes along with it, but the maximum value of the output doesn't change. So in this way, like despite the stochasticity in the hidden layer, the result stays correct stably. So this is the mechanism through which that the neural networks can have a stable performance in presence of noise. Yeah.
So you're reading the optical signal, and then you're transducing it. So you're sending another optical signal. So you're going from optical to electronic to optical to electronic.
Yes. In this case, yes. Yeah, that's a good question. So basically, say for this demonstrations, it's like say there's a transduction step. So the nonlinearity is mostly done in electronics. But here, another notable feature is that there's no nonlinearity needed because the photon detection is kind of clipping the 0, 1 photon. It's kind of giving a nonlinearity here. Actually, there's a subtlety here, but yeah. But yeah, if you have a question, we can discuss more. There's a subtlety in terms of this kind of projection, kind of nonlinearity. But here somehow we get rid of digital nonlinearity at all. So but I would say besides the single photon detector, what really makes this whole thing working is a better training algorithm. So the reason why we could push this limit is because we model the photon detection process into our training pipeline. So when we do the backpropagation of error, and that allowed us to the model to be more robust with noise. And then just a quick look at the results is just basically saying we are pushing for the intermediate layers. We are pushing the energy consumption like by another 100 times. But because there are some like the last layer is still in analog region instead of a single photon region, so the overall energy improvement is maybe about 10 times. All right. So this is like basically state of art on this when this optical energy scaling law breaks down. But based on this, it's at this point it's like scientific curiosity. It's like say, okay, it's practically speaking, we're never going to run into this region unless we're doing some kind of thing like low light sensing. But then based on this, is just to say, okay, can we? The second question is just that can we? Based on this, do something useful tasks, and this is what I'm going to talk about. So to show the useful tasks, like we went for this large language models, and for 3 years ago, when we started working on this, it was still an exotic object, but nowadays everyone knows it's basically some autoregressive models like ChatGPT, and then it's just predicted token by token, and it's usually based on for language, so you basically predict the next word, and it's based on the context, the correlation of information between different tokens, and therefore you need to compute something that is called attention matrix between like every pair of words, and that takes a lot of computation. Our focus, to show that the optical hardware has enough precision for large language models. So we first started with a transformer, and transformers they feature very long vectors, as we showed, because of the context usually consists of many tokens. And we use a relatively small transformer at the GPT-2 level. It's like this is like a 1/12 of the depth of it and 1/12 of the width of it, but it's considered a very small large language model. And for this model, we use the so-called quantization aware training to train it. But at that time, our hardware was not good, fast enough, so we could only run part of the model on the hardware. But that was enough for us to know if the precision is good enough. So for the part of the hardware like attention and feed forward layers, we're on the hardware, and then what we did was we plotted its error distribution histogram. So in this way, we know that how much error we are expecting from like a practical hardware. And then based on these error models, we try to predict the entire model performance. And then we see that there's one thing interesting is that, overall, we see that, optical analog resolution is perhaps enough for running language models compared to infinite resolution. And also interestingly, we see that it has different reliance on different parts of the model. For example, like it's for the attention layers, it's less sensitive, but for the feed-forward layers, it's more sensitive. And I personally, I'm now interested in studying like in more details now which part of the model are more sensitive to low numerical precision. And also this happens to be an area machine learning people are also very interested in understanding. So I would say based on the understanding that these models can possibly run optical hardware, so we build an energy prediction model. Say because the whole point is to show the optical scaling law. So for example, if we build a large enough, if we manage to build a large enough optical hardware for something like ChatGPT, how much overall energy benefit we would get. And here we're just showing like for whole system level, we would get about 100 times. And that's really comparing with like futuristic GPU versus like optics with existing like ADC, DAC energy consumptions. So it's not a big factor because of all this kind of practical energy consumptions. But if we build larger models, the energy benefit factor would be bigger. So really what my lab is doing right now is that we are building some integrated photonic setup so that we hope to be able to fully run a transformer model on optical hardware just to show people that this is possible. And then if possible, we wanted to do some training on it. So yeah, this is so much on this like optics for purely for computing. With all this kind of investigation, I think we learned that optics can have a non-trivial computing power, and then but in my opinion, like what is more near future plausible use of optical computing is actually for sensing purposes. So, there were a lot of applications that requires the sensors. Actually, we are facing a so-called the sensor gap, which means that all these sensors are producing more data than we can ever store and process. And so there's a projection that, as the time goes by, the data, there will be a data overflow. So therefore, like one way we get the inspiration is from by neuromorphic sensing, which means that we want to reduce the data before it reaches our data storage. So for like on average, like 10,000 photons hit our eye, but only generated one spike traveling down the optical nerve. So this is essentially the biological solution to an overflow of visual information. So it reduces to only it reduces like megabits of information per second to only 100 bits per second, and only concentrate on important information so that we can clearly make a decision in response to the environmental change. So a selective, salient, sensitive information reduction is an essential part of intelligence. And for optics, we can really use them to reduce information in the optical domain. So the philosophy is just essentially say, in a conventional machine vision system, we take image of a high resolution image, and then we first take a high resolution digital image, and then pass it through a digital neural network and to extract the essential information we're interested in, which is usually tend to be very sparse in images. Right, so here it's like 100,000 pixels. So here we only need two numbers. So and therefore, like the motivation is that can we instead just put an optical neural network in the optical domain, and that reduces the optical data in the optical domain, which means it converts a high dimensional image into low dimensional feature space. And then only at that point, we start to use photodetector to convert to electronic signals and then put a very light digital backend on it to extract the information we want. So this is what we call imaging sensing. with optical neural networks. So one key thing we want to stress is that, to better like compress this information, we think it is necessary to have some kind of nonlinear functions on light field. Just linear processing might not be strong enough in most of the cases. So the paper is just essentially trying to demonstrate that point. But before that, I just want to show there were many prior works in this field as well. Even including using integrated photonics and but really, it's like the field is going towards the direction, say, trying to implement, put more nonlinearity into the process. So for our architecture, so we basically used a three-layer neural network, but the two are like linear layers, and then there's one nonlinear layer in between. And then it's a simple task, and we really wanted to stress that it can process like natural light reflect from the physical objects that is like broadband and incoherent. And here is the prototype setup we made. And the setup achieves like quite a high compression ratio. It's normally it achieves like 400 times compression ratio, but at some extreme cases it can go with 800, and then we only measure like 4-dimensional output, and then based on that make a decision. So a little bit on the engineering part, it's actually based on all very known like principles. So for like optical matrix vector multiplication, we just use like light field inspired way. Just we make optical copies of the same image and modulate each copy differently, and we get element-wise product, and then we focus them. So these are just some illustrations of like micro lens arrays. And they are basically, I'm saying they are good for doing optical fan out for 2D images, and it has some 3D information, and it's at the highest efficiency of optical fan out as possible, and it works both for coherent and incoherent light. So it's a very good solution for free space processing with images. So, and for the nonlinearity, we used a solution, which is like a photon multiplier tube, like an image intensifier. So it's a spatially resolved photon multiplier tube. It takes a light in and onto photocathode, and it gets some electrons, and then it amplifies the current, and then hit on phospholayer, and then generate like output light. So it takes like light as input and light as output. So it can be, in principle, cascadable in the optical domain, and with some kind of amplification to compensate for loss. And also has high resolution by definition because the image intensifier, and also it provides a saturation type of nonlinearity, and it can be reasonably fast. So that was a good enough solution for our demonstration. So this is something what it looks like on the other side of the image intensifier. So one task we really want to show is that this works for real life applications. So essentially, with a 3D physical object, we 3D printed it in a lab. As you see, the setup was too large to take it into the outdoor. So like we used the 3D printed version, and then we shed the light onto this. This is the photo of the speed sign limit, and we show the classification performance as a function of viewing angle. And here we really want to show that for the nonlinear optical encoder, which is just the neural network front end, it outperforms linear encoders, with the same kind of digital backend. So we want to show the value of adding nonlinearity in the systems instead of keeping them purely linear. And then for second practice, I think for me, it was more convincing. It's like when I start to see the reconstructed image from this compressed version, because whenever you do this classification, it's doing right, and I can't keep wondering, just like whether there was some mistake in the code that made us believe it was correct. But once we start to reconstruct the image, it start to be obvious that okay, indeed, even though we compress it to 4 dimensions, it still contains a lot of information. So here we're just using a so-called autoencoder structure, right? The optics doing the encoder and the digital doing decoder. And here just to show some interesting examples of image reconstruction. It keeps some feature, like for chairs, it keeps left-facing and right-facing features, even though the details are not quite right. And for the hurricane, the basic contours are correct, even though the details wrong. So, and that shows us that with this much information retained through this compression, indeed, it's possible to achieve high classification accuracy. And then comes to what I'm interested in my lab right now. One interesting. I think the real application for this is just low latency, super fast machine vision, and I think the application in this cell sorting in flow cytometry. In this setup, like you flow cells through a laser, and you take an image to classify them by morphology, and you need a really low latency, really high throughput here, and this is really challenging for current like imaging and processing systems. And I think this is where like optical compression and classification can be really useful for. Just a word on saying that, traditionally people do not take an image for flow cytometry. They just measure fluorescence. But now when they start to take an image, the stuff easily gets really, really sophisticated. But with this optical classification, we could take the data set from this like first image-based cytometer, and then we put on into the input of our setup, and we use our optical encoder to sort it. And then we show that with a nonlinear optical encoder, it could achieve 93% accuracy on 5 classes of different cells. That really gave me hope that it can be translated to particularly competitive performance. But my lab is currently working on a different architecture, quite different architecture from this, and we really want to show it on real 3D cells to show that it's a sorting performance. Another thing to show is that this is like a so-called unsupervised learning on this cell classifications. So there's some the idea is that this like we don't know every kind of a cell we feed through the system. Sometimes they are just very rare kind of cells we needed to sort out. So we can usually use the supervised learning. So for the system, if it preserves enough feature, actually it's possible to do unsupervised learning, which means that it can cluster this different classes of cells even without knowing the label. Here just showing that this compression indeed preserves the enlarged image features so that they can be separated in the latent feature space. So one last thing to say about this, well, I will leave it later. So one last thing I want to say about this is just say, I think a lot of people are interested in quantum sensing, and that's the reason why you invited me here. In the end, I want to say, actually, I have more questions than answers in this field because we continue to work on image sensing with quantum light. The whole idea of this is quite simple. Is say with coherent classical light, you have uncorrelated spatial modes, and then you get some information, photon counting on spatial modes. You can process it a little bit with optics, and then you try to extract the information from it. With quantum light, the extra degree of freedom you have is like you can engineer the correlation between these spatial modes, so that with this correlation, you get some extra information, and in principle, you would hope that you get better performance at image recognition. And no, technically speaking, like it's quite feasible to engineer this kind of spatial entanglement. You just engineer the pump to your like spontaneous parametric down conversion, so that you can engineer like almost arbitrary spatially correlated light. And if the stronger quantum source you make, the higher order correlation you can have, and then the more order you can extract, the more information you get. But really, the question is that now we are faced with a machine learning test. Basically, we wanted to recognize patterns, and then it is really becomes very hard to quantify like what kind of advantage we are getting from these quantum sources. Because in simpler tasks like hypothesis test or parameter estimation, there are theoretical bounds like Chernoff bounds, like Cramer-Rowe bounds that we can say that in certain conditions quantum has unique advantage, but like in machine learning tasks, it's like really far away from the bounds. It's really hard to say that once we put the quantum resources in, do we actually get any advantage? So this is still like a question that is bugging me. I wanted to raise this question to this audience to see if anyone has any thoughts, because for all these experiments, like in the end, when you want to submit results for people to review, you cannot avoid this question. So how do you actually quantify to show that this quantum system resources is being used in a way so that it cannot be replaced by a classical system? We have some preliminary results, but I think now we are doing very heuristic way. We're trying to analyze like a principal component analysis, but I think after thinking about it, I think maybe we can discuss after the talk, but instead of putting it here, because I personally still have some questions about the results. So anyway, in the end, I just summarize, for the chunks of work we have done, I really to show that, to prove the point that the optical neural networks can work in a way that is highly resilient to noise and working in the single photon regime, and they have a energy scaling that's very favorable for large models. And also, I think they are really good for low light sensing, and that requires extremely low latency. And this is a direction I think I want to pursue in the short term. But last but not least, it's like, I'm still recruiting students in my lab. For those interested in these directions, you're welcome to contact us. We have some crossplay, interplay between data science and the photonic centers. Yeah. Right. Thank you.
For comment all the way to so I appreciate you being here. I'm curious. So these optical analog computers seem to come up every 20 years or so in the literature. There's a cycle, and every time there's something wrong with them.
Yeah.
And could you talk about the limitations of your kind of proposed system? I mean, be honest, I guess, is what we are expecting here.
Yeah, so it comes up every 20 years, but I actually came up only once before, and then so yeah, that's a question I always get. So and every time it want to come up, electronics start to become much better. So at least it does one thing, like give pressure on electronics to push it to do better, creates some computation. So, but I would say currently what we are facing, okay, so this time the reason why it comes back is because suddenly it's so synergistic with machine learning, like larger scale linear processing. This is like one thing optics can do well, and one thing that machine learning needs, right? Like there are things we know optics cannot do well, like optical memory, like optical transistors. That was like something like 30 years ago. So this time people wonder, it's like, okay, with this opportunity, can we do a little bit differently? So currently I would say the bottleneck, there was a bottleneck, scaling is a big thing, right? So, it's not just engineering, like free space has the bad image that is a huge bulky, but actually it's doable. For on chip has an image that being scalable, but actually it's disappointing so far. But the real issue is that optical wavelength is huge compared to electronics. So the
you need to think about is like, can you make a trade-off to make a larger system, but still like perform as well? Because for GPU, it is the chip is small, but the cooling is huge, right? For obviously you can indeed your computing part is becoming bigger, but if you can get rid of that cooling system, maybe the end result is not that bad. Like free space, like transceiver plug, it's not very huge, so it's not the end of the story. So but for I would personally say still there's not one architecture that we can just converge on. Say that we just keep scaling that, make it large enough so that it will just surpass the digital computing. And currently, our estimation is that n dimension, like crossover point, needs to be a couple thousand. That means the matrix size is like a couple million, more than million elements. And that's kind of challenging. So to change that crossover point, basically, either we need to have a breakthrough in ADC, DAC that suddenly it's a lot more efficient, or some other things that will make that crossover to happen earlier. And this is one basically engineering obstacles, and then to achieve that crossover takes a lot of investment, and this is really just like startup company's job. Another thing is just the way to think about computing, right? So like if you think of analog computing, it has not been accepted by industry as a standard. People worry about analog hardware having variations. And especially for distributed computing, you wanted to distribute the model to different parts of hardware. You want them to be identical, not with a variation. So that's a problem need to be solved. That's also mentality needs to be changed. And until digital computing hits a wall, people are unlikely to change their opinion. Just like electric car, it makes sense, but it's only when like fossil fuel goes to an end, people start to really think serious about electric cars. And also there's a training problem with analog computing systems. It's just say, a lot of times we cannot directly use background propagation. We need to think of other ways to train it. Then the question is that is it as a scalable and does it achieve absolute as well a performance as a digital computer? Like there were written papers claiming methods like it can scale to language models, and really just it takes time to see if how well it stands. So so there were couple levels of challenges with this.
Thank you. This is thank you for this honest, very honest answer.
Oh, yeah. It doesn't hurt to be honest, but despite all this, I personally is quite optimistic because because I'm in the research field. Yeah. I'm not like starting business. Yeah.
Hi, Kevin. I'm from the Dr. David Brady Bunch lab group. I really like your talk, very thought-provoking, especially mentioning the Nobel Prize autoregressive models, ChatGPT, and especially the stochastic part. Something my colleagues and I like to say is there's no flaws, just features. And I was wondering, given DALI and diffusion models, right, the biggest bottleneck in that research for generating images is the iterative process of adding Gaussian noise from hundreds of iterations to thousands, and then doing it in reverse. I was curious if you've been exploring or heard of any research where this could be done faster optically than electronically.
Yeah, I think that's noise, how do we use the random as a random source in generating models, especially basically for image, you put the noise in your feature space, and then you generate the details, and then it just give you different style, right? So it's all about this, but once you dig deeper into the architecture of a diffusion model, it's physics inspired, but it's still not. It's still not trivial to map it to some exact physical processes. So therefore, like I look into that for a while and not decide not to work on it, but maybe there's something. But generally, I agree that how to leverage this noise for generating like truly random source for generating content, I think it's a thing to explore. It's just basically you need the randomness, you also need the structure to generate it, like right. So you feed the randomness into a structure to generate it.
You mentioned illumination, maybe that could be a process.
Illumination?
Like when you were showing coded illumination in your slides,
Yeah.
maybe that could be the process of introducing noise. For imaging.
For imaging, yeah, but the noise is already in your detection. Like if you go with, if you can count each photon, then the noise is already there. You don't need to introduce extra noise into your system. Yeah, but yeah, I would say, you know, I don't think I spent enough time to figure out the wide diffusion model and work, so therefore I think that's still an opportunity there.
Right.
Yeah.
I mean, it'd be powerful to be able to take it and make it in any camera, right?
Yeah.
It's been well over 10 years since Shalev and Boltaseva at Purdue were doing optical metamaterials, optical metasurfaces. And I don't think it ever went anywhere. Have you, in your labs that you've been working in, even explored them? Have they been of any interest at all in this sort of thing?
So for optical metamaterial, yeah, I talked to many people, and also there are several, two people in my department also working in this area. Naturally, we talk about the possibilities and the computing potential of the metamaterials. So my fantasy about the metamaterial is always about its ability to process different wavelengths quickly, so that you can kind of do a single shot processing of multi and hyperspectral object images. But the reality is that the actual metamaterials can be made these days. It's very hard to design and fabricate so that it processes each wavelength in the way you want. So I think that's an engineering issue. Once that is possible, yeah, I would say, having a couple metamaterial layer, they process different wavelength differently, and then you have like wavelength information in addition to spatial information. That'd be great. But yeah, but so far I have not found anyone can confidently say, yeah, I can make it.
Right.
Yeah.
No labs that you've been working in have attempted?
Not the template, it's just like find people, they do this and they're asking, can you do this, and this is not the easiest, the first thing to do. Yeah. But I don't have deep enough understanding on what is the technical challenge there. Yeah. Yeah.
We have a question.
Yeah.
Thanks for the very great talk. So I noticed that the most of your work is focused on monochromatic image. And we all know that the optics, the background of electronics probably has a really large bandwidth. Do you have any plan to adapt your method to a multicolor system so that you can do this vision task?
So for vision task, yes, actually had a multiple wavelengths. Like here, we just say we are not utilizing information for multiple wavelengths, but for here, in principle, it's all like a natural light, a broadband light, incoherent light. So it's just basically say it works with very broadband light. It's not picky about the wavelengths, but yes, indeed, we are not using information from different wavelengths. But yeah, I think for integrated photonics, like wavelength multiplexing can be useful, saying to increase back capacity maybe by 10 times, but not by 1,000 times. So yeah, that's like different context. There's different wavelengths plays different roles. Yeah. But for the meta surface question, back to it, is like that's basically the intention to say, if we can use the information in different wavelengths differently, that'd be great.
Question? Let's give a hand.